Okay. All right. So, good afternoon, ladies and gentlemen. I hope you are all doing well. Today, I'm gonna be talking about our fourth tutorial, and if you remember correctly, we are gonna be talking about this tutorial, which is available on, which will be available on ELE, and it will be available on Google Classroom. So, however, what I felt is that if we want to solve this example or this assignment, we really need to understand some basic concepts, and then you can easily follow the steps on TSM. So, for example, how to set up a model. You just need to remember what we have done, in setting up a model, and how to do, Monte Carlo exercises and so on. And everything is available on this, the details of how to use TSM is available on this kind of exercise, okay, in this sheet. Now, what I really want to focus on is this presentation, which I think it's quite important, and then we can go into the details of using it. So what is here so let's remember some definitions and terminologies. A simple random sampling uses sample of size n from population of size n, so this is small n and this is a big N, to obtain data that can be used to make inferences about a certain characteristic. So what I want you to think about is that, let's say we have a certain population. Okay, let's say, for example, something that is somehow unknown to you. For example, let's say that you are a student at the university, and you really don't know how much the gym membership costs. So you know that you are with some friends. This is your friends, which is a subsample because they represent a certain group of the students in Exeter, in the University of Exeter. And those students, you can ask them how much each and every one is paying. So you are asking only a sample of size n from a population of size n, which is a population of how many students are there at all the university here in Exeter. And suppose that from a population of, here for example, I gave an example of the population of 50 banks accounts. Okay, so we have 50 bank accounts. We want to take random sample of 4 accounts. So my sample size is 4 here, so this is n equal to 4, and the big N, we are assuming here it's 50. Okay, so this is an example. If I ask you how many how many samples could we really generate from 50 bank accounts, how many 4 accounts could we select? This is known in mathematics as a combination, which is defined. You can look at it. Usually, assume that the sampling process. So this is collecting sample. So sampling process means that you are collecting samples from a population of n, of size n, which is in our case 50. And this is usually occurring without replacement. There is, C n by n ways of selecting n elements of big N elements. Okay, so what I want you to think about an urn. Okay, an urn that has so many balls in it. Okay, some of them are blue, some of them are red. So okay, and basically what you want to do is that you want to pick them up. You want to pick some of those balls up, and you want to create an artificial urn. So here, for example, here I think that I have 5 balls, but here, like if you do, a random sampling of 2, you will have, only like sometimes you will have either, one of them is red, the other is blue, or you might have them as, both of them are blue, and so on. This is known as sampling. This is sample 1, this is sample 2, and so on. Okay, it could be like this is sample 3. Okay, so you can have, in this case, you can have a C5 of 2. Okay, usually it's given as 5 factorial over, 2 factorial times 5 minus 2 factorial. Okay, so don't worry about this. It's just that I want you to remember those kind of stuff. In each random selection, so this is a main word that we want to know. In each random selection of a sample, we are assuming um, that each individual selection have an equal chance of being selected. So basically, if you are a data, a guy who collects data. So let's say you are trying to study some, wage and education phenomena, right? Okay, and you are trying to collect data on each and every individual. So what you do is that we are assuming as a researcher, you have, each and every individual on planet Earth, or actually the ones who at least surround you, can have equal chance of being selected. Okay, so this is what we mean by random selection. And simple, when we say simple random selection, this means that we are drawing chips from a box and using the random number tables. This is the same idea as the urn that I just mentioned to you about. And the sampling distribution is derived from the set of values taken by the taken at random from the population. So when we are, we are interested in knowing the values of a certain random number, or like you have taken a certain set of balls, and you are trying to understand how many of them percentage-wise, how many of them would be blue and how many of them would be red. Okay, so for example, if we go back to our previous table, we said here, for example, how many in general the population would be of red would be 2 out of 5, right? And the blue, this is for red, and for blue you might have something else, right? So blue is 3 out of 5, so the sum of them is going to be equal to 1. So when you are randomly selecting only 2, so for example here the probability of red is equal to what? 1 over 2. So it's a bit far. But you can see if you increase the sample size, you are going to get closer to the population parameter, or the population percentage of how many red balls are in your urn. So when we achieve this, when we find all the possibilities, we're going to have a certain distribution, right? If you remember the histogram and so on. So we're going to go into the details of this, just that I want you to remember what we mean by sampling distribution. A sample distribution represents a distribution of the sample statistic for certain randomly chosen members of the population. So sample statistic can be the average. So the sample statistic can be the average, the estimated coefficient, and the t-statistic and the f-statistics. All of these could be known as a sample statistic. So if you remember, what we used to do when calculating an average really depends on how many observations. So remember that you are collecting only n observation. So what you are doing is that, let's say you remember the idea of, if you still remember the idea of, finding how much the cost of a membership of a bank, membership of a gym costs. So if you remember, when we had, you're taking a sample of the university students at Exeter and you're asking each one of them. So let's say you ask one guy and he tells you that it is, or Alex, he told you that he pays X1 units, X1 dollars or pounds, a year. Some other guys tells you he pays about X2, and so on. So the mean would be the sum from xi, from I equal to 1 up till n, of course divided by 1 over n. So this will be your sample mean. And it would be a nice idea to illustrate the intuition with a basic statistic, then generalize the intuition to estimated least square coefficient, which would be one of the questions that you're going to be asked in the tutorial 4. So consider the sample mean, and this obviously we are talking about here n. Now I think I should have put small n over here. It's just that I want you to understand that this only represents the sample. Okay, so when we say sample mean, it represents the sample that you have collected. And where each of the xi is observation selected randomly from a population of true mean mu. So this will be the actual price that you have to pay for the membership if you were to call the gym and ask them how much should I pay for, you know, a year, they will tell you this amount of money. Okay. The sampling distribution of x n bar is a probability distribution of all possible values of the sample mean. Okay, so when you do a lot of samples, so let's say you selected some samples. Okay, so you selected a lot of samples, and each of your sample have, let's say, five students. Okay, so you selected lots of samples. You will have here, you will have your first x bar, which is based on 5 observations, but will be your first sample. This will be your second sample of 5 observation, and this will be your third sample of 5 observation. Okay. We believe that as n goes to infinity, as your sample size grow, your x bars should converge to what? To the population mean. Right? So here what we have done, we consider the following relative frequency distribution of x bar 30. So we collected, you know, so many samples of 30 observations, and we compute for each and every time from that sample we calculated the average. So we have taken actually 500. So we have taken 500 simple random samples of size 30, and this was the annual salary. So here we are talking about salaries of we are talking about salaries of managers, and we have seen that if how many times did the salary of managers within a 30 sample belongs to this annual belongs to this interval of annual salary. It turns out to be, for example, we have 2 for that, 16 for this, and so on, until we reach a total of 500. Okay, so we have 500, 530, we have 500 samples. So remember that we have, this is sample 1, you have 30 points, this is sample 2, you have 30 points, this is sample 3, you have 30 points, and so on, and you have until 500. So this is 1, 2, 3, up to 500. And for each one of them, you calculate the mean. And if you do this, you will find how many means? You will find 500 means, right? Of 30. And when you do this, you will compute the frequencies, and then you can compute the relative frequency. So the relative frequency is nothing but 2 divided by 500, which is equal to that number, and so on. So the sum of the relative frequencies is equal to 1. And remember, why do we need this? Because the sum of all the probability distribution should be equal to what? 1. So that's why in statistics, we really prefer to use a relative frequency. But to ignore this right now, let's see how the relative frequency on the y-axis and the value of x bar, this is the value of x bar, not the value of x, will look like. So this would be the distribution of the x bars. So now of course I'm referring here to x bar as a statistic. But remember, when we are talking about beta hats are actually a function of what? Your sample size. So this beta hat usually represent, if you plot the distribution, it usually represents this distribution. So if we gonna be estimating it, smoothing this, so the more you have data, the more it's gonna be smoothed over the time. So here is the smoothed value, and we believe that the sampling distribution of the sample mean as n goes to infinity will approach what? Will approach the population mean, right? And if you add more samples, or more and more data points to each and every sample, we believe that this will converge to what is known as the normal distribution, and or the t-distribution, depending on what are your underneath assumptions. For now, let's say we are assuming that it converges to the normal distribution with a mean of mu and the variance that really depends on the how much this distribution is dispersed. Okay, so relationship between sampling distribution and the true distribution. Suppose that we compute 100 means of 100 different samples, right, of size 30. This is what we have done. So we have x x31 bar, x32 bar, until x33 bar, and so on until we have x30 100 bars. And we actually plotted the distribution of each of them. What we can say is that if we computed the 95% confidence interval of each and every distribution, we believe that 95% of the time, because we have 100 samples, right? So this is sample 1, this is sample 2, this is sample 3. You could also have, sample 4 somewhere over here. This is a 95% confidence interval. This is sample 5, and so on. We believe that if we do this 100 samples, we think that 95% of the time this population parameter will belong to what? To those samples. And this is why we really care about doing Monte Carlo exercises. So the Monte Carlo exercise will allow us to do this sampling distribution and create a lot of artificial samples that will make us understand if this mean belongs to the interval 95% of the time. If it does, then this is a very good thing, and basically we can rely on a particular sample, because remember that in reality what you do is you only have one sample, right? And you calculate the 95% confidence interval, and you were testing the null hypothesis if the true parameter equal to 0, or the alternative parameter is that mu is not equal to 0. And that's why we always tell you to find the 95% confidence interval. So that's what we mean by 5% significance level. And we tell you based on that, tell us if you reject the null hypothesis that that the beta, for example, is equal to 0 or not. So what you used to do is you find the beta hats, and you take the t-statistic, beta hat minus beta, over the standard error. Over here, it's different when we talk about sample mean. This is because we have different understanding of the statistic beta hat. So the beta hat has a different shape or a different function of the data. Suppose that we have done sampling on annual incomes of managers, and we select a simple random sample of 100 managers, okay, instead of 30 originally considered. So what we did is for each and every sample, remember I told you that we have 30 observations. Now let's say we have 100 observations per one sample. So we have how many samples? We have 100 samples, right? So this is, we have 100 managers in each and every sample. Okay, this is 4 up till you reach 100. And I would like to ask you one question. Intuitively, it would seem that more data provided by the large sample size, the sample mean based on 100 should provide better estimates. So when we have more data per sample, we expect the distribution of the x bars, okay, to approach more the population parameter, and it will give us a better estimate of the population. And we will see this like this. So remember when Professor Namyoun plotted this. So what she said was that the more we have data, the more things become narrower. So this would be the population parameter, and you will see that the more you have data, the more it becomes narrower. The distribution, the relative frequencies become narrower and this will be called the accuracy. And the accuracy will be measured by what is known to us as the standard error. Okay, I'm gonna talk about this in a minute. So the standard error of the mean is also known as the accuracy of the mean statistic, and sometimes it's given by this formula over here. And as you can see, as your sample size grows to infinity, what will happen to this? This will go to 0, right? So this becomes, you are very much accurate. And this will, usually we would like to say that this converges in mean squared. I don't want to go into the details about it. It's just that I would like you to understand, the basic concept of of increasing your sample size, and why is it very important that the more you have data, the more accurate you are to the true. All right. So now that we have spoken about this, I want you to understand that when it comes to least sampling distribution of the estimator of the coefficient in a linear regression model, you have to understand that beta hat that you know, the way you know it, could be, it's actually a function of lots of other variables, which includes, so I'm just gonna, so beta hat, the way you know it, is actually a function of what? Of your observations, which is your x's. So x1, this is the x variable of, your first observation, your y1, which is your dependent variable of your first observation, x2, y2, all of these, it's a function of all these, vector of observations, right? So you have, how, depending on how many variables you have, we're assuming you have n sample, the sample size is n. And because this function could be very different. It could be representing a certain beta star, which is another function of the same observations. So you could have a lot of other functions, which is a function of your data samples. So the sample distribution of the OLS estimator, the one that you already know and familiar with, we call it OLS, which is the ordinary least square estimator, but sometimes we call it the BLEU, which is the best linear unbiased estimator, depending on the assumptions. So if those assumptions break down, as we have discussed in my lecture, which is lecture 6, then beta hat might not be the best linear unbiased estimator. And we are going to be seeing all of this in the following tutorial. I just wanted to record this session to make sure that you are really familiar with what we are going to be seeing right now. So the distribution of the values taken by beta hat and repeated sampling experiment is given as follow. So unlike the sample mean, there exist many possible ways of finding an estimate of the true coefficient beta. So for example, here I gave you two examples, which is beta hat and beta star. And you will see that the expected value of beta hat is given by beta 2, and this is known as a sample distribution of beta 2. And as you can see, this would be the the population. This is a true parameter, and this is the estimated parameter. We are assuming that this is a sampling distribution, while for beta star, this is a sampling distribution of beta star, and this is the mean, which is beta 2. Now you can see that this is much more dispersed than this, than this OLS estimator beta hat, and obviously there is an intuitive reason for that. So if we plot them across one another, you will see that you have beta hat and beta star. These are the sampling distributions of beta 2 and beta 2 star. Okay, or what I meant here, beta 2 hat and beta 2 star. And you can see that there is a difference. So if I ask you which function will you select, is it the beta hat or the beta star, you should obviously select the beta star, because the dispersion around its population parameter is closer. So the accuracy of beta 2 hat is much narrower. So it is more accurate than the one that we have about beta 2 star. So this is well known in econometrics. It is evident that the least square estimates are a function of the sample data, which I just mentioned, but the data changes from sample to sample, right? Yes, because of the random sampling, because we are selecting different sample, like each and every researcher select different sample, and we are assuming that the population parameter lies within that sample. And therefore, we need a measure to inform us which estimator or a function of sample data is better, more precise, and we can sometimes call it more accurate. So it could be easily seen that the variance of the beta would be the best measurement of informing us which estimator is better. And therefore the precision, which is also known as accuracy, so this is a very important word, which until recently I was aware of it because I used to know it as precision or efficiency, but it can also be used as accuracy. of the estimates is the standard error of the least square estimator. So basically the precision or the accuracy is the estimate of the standard error. Okay, so basically the estimate of the standard error, so the variance of beta 2 hat, it is estimated, and it is going to be the square root of that. Okay, and you can easily, this is known as a standard error of beta 2 hat, and this could easily be seen in TSM, right? So whenever you run a regression, you will definitely see in TSM or any other statistical softwares, you will see that it's also reporting the standard error of beta 2 hat. Okay, therefore the accuracy of the estimator is how precise the estimator measures the true population value. And since we are talking about accuracy, I just need to draw your attention about what we mean by the biasedness. So the bias of beta hat is beta hat minus the true parameter. This is not the same as accuracy, where accuracy means how much this value over here converges to what, to zero, basically, right? To zero. Okay. All right. So good afternoon, ladies and gentlemen. I hope you are all doing well. Now, going back again to talk about when to reject and when to not to reject the null hypothesis when it is true, and when shall we reject or not to reject when the null hypothesis is false. Now, this in the literature have been studied so often, and here I think that we have covered so many topics about this particular idea. Now, I want to remind you that usually in the literature, we are very much committed to type 1 error. So we are really, really worried about this particular type 1 error here. And that's why we really care about, it's usually always designated with alpha, where alpha is called the level of significance, and it is usually between 0.01 and 0.05, but the one with 0.05 is usually the most used in the literature. And the probability of so basically when we reject the null hypothesis, when the null hypothesis is true, we call this, you have committed an error, and we call this to be type 1 error. And this is important. Why? Because this is what we are really interested in, is the null hypothesis, and therefore we really want to do not reject when it is true. So in this case we commit no errors. Having said that, I want you also to be aware of the power. Now I'm going to go into the power, but it is very much related to type 2 error here. So here we are assuming that the null is false, okay? And we do not reject the null hypothesis. So this means that we accept the null hypothesis although it is false. This means that we committed a type 2 error. So as I just mentioned, the probability of a type 1 error is designated as alpha, and it's called the level of significance. The probability of type 2 error is designated by beta. Okay, so and the problem here is that we need to really understand how to, beta is being computed. The probability of not committing type 2 error is called the power. Okay, so the power of the test is when we do not commit type 2 error. So in this case, having spoken about this, is if we go back here and we mention that this is beta, right? And basically when we reach this kind of conclusion, it is, like we want to know how many times we reject the null hypothesis. When the null hypothesis is false, is going to be called the power. And therefore the power to us, because remember that the sum of these two is equal to 1, it's going to be 1 minus beta. Okay, so this is what we mean by the power of the test. This means that we are always going to be getting to the right conclusion this means that we're going to be rejecting the null when the null is false. So I mentioned these stuff. And the probability of not committing type 2 error is called the power, and the power of the test is its ability to reject a false null hypothesis. the power of a statistical test is 1 minus minus the probability of committing a type 2 error, and this means that it is 1 minus the probability of accepting the false null, which is 1 minus beta. Now this is what I have about power. Before moving to Monte Carlo simulation, I want you to think about the power as follows. So I'm gonna talk. So I just wanna remind you that when we have, when we wanna reject the null hypothesis. Okay, so I'm gonna go a little bit backwards. So when we want to reject the null hypothesis, okay, we want to reject the null hypothesis when the null hypothesis is true. We call this to be type 1 error. Okay, we call this to be type 1 error. Now, I want to give a certain example that I believe many of you are aware of. And I think it is good to, to repeat some stuff. So consider we have, a certain mean, x bar, that we believe that it follows a normal distribution with a mean of mu, which is, we can give it whatever it is. Let's say it's 50, and the variance of 100. Okay, and if you know that this, remember we have spoken about the sample mean, and if we would like to draw the confidence interval for that, you remember that it is given by, remember the t-statistic where we said that it really represents the t-statistics. Here it is x bar minus the mean over the standard error of x bar. Somehow it should remind you of what we have studied so far about the t-statistic, which is given as beta hat minus beta over the standard error of beta hat. Now, I'm saying this for a reason. I'm saying this because we need to somehow dwell into the details of how to find things clearer. So this t-statistic somehow, the standard error, I think Professor Kim have shown to you that this is equal to the square root of the variance over the sample size n. Let's say our sample size is about 25. Okay, so our selected sample is from the population is 25, and we know that the variance is 100, so this is 100 over 25, which is 4, and therefore this is equal to 2. And we know that the t-statistic should be between what and what? Between, the 95% confidence interval. Let's say here we are assuming, that, a 95% confidence interval, and therefore we are looking at, the 95% critical value, which that it's 1.96 for the normal random variable and minus 1.96. So basically our x bar minus the mean, which is in our case it's gonna be 50, it's between 1.96 times 2, which is a standard error of x bar, times minus 1.96 times the standard error, which is which is 2 in our case, times 2. And therefore x bar is nothing but 50 plus 1.96 times 2, and 50 minus 1.96 times 2. And accordingly, we can say that x bar should belong between where and where? It should belong between, so it is between 53.92 and 46.08. And we said that this would represent, so if I'm gonna be drawing, the curve of the, the probability density function, it should look something like so. So if I draw this, I wish I draw it with another color. If I have a black color, that would be good. So this is the axis, you know, if we draw this, you know, the curve, okay, this is a normal random variable. So this means that here, which is 53, and here, which is 46, this means that the area over here should be equal to what? Remember, it should be the 95% coverage. So this is alpha, which is equal to 5%, which is 0.05. This would be, if x bar lies here or there, we reject the null hypothesis that mu is equal to what? 50. So our null hypothesis is mu equal to 50, and our alternative is mu not equal to 50. So if we said this, if you agree with me that, you know, this is a null hypothesis and this is the alternative, then more likely if we simulated this data set, if our x bar, the calculated mean, turns out to be either in this area or that area, and we are testing for the null hypothesis, when the null hypothesis is true, it should be 5%. Otherwise, it becomes what? More than 5%. So let's say now we are testing for a difference. So let's say that we take these stuff are as given. Okay, so actually the true distribution is being distributed from a 95% confidence interval, okay, of this mean. And what we want to do is we want to study what will happen when we have a distribution that, you know, was generated from, you know, originally. So our null hypothesis is we are testing is something like, let's say it is 48. So if we are testing for 48, and remember this is the mean, which is 50, then this means that we are over here. This is the mean now, the 48, and this distribution looks something like so. You can see that we reject the null hypothesis. We reject the null hypothesis when the mean should belong over here or over there. Now we found out if we want to do the calculation, it turns out to be that this, for this alpha, the alpha, which is rejecting the null when the null is true, which is, if you remember, I'm just going to show you here. I'm talking about this area, so I'm going to be rejecting the null when the null is true. I'm talking about this type 1 error. It turns out to be that, you know, because it is still in the acceptance, this would be the acceptance zone, if you remember. Right, so any area that belongs between these two is gonna be called the accepting zone. So I'm gonna color this with a green color just so that it makes sense. This is gonna be the accepting zone. Okay, so we're accepting the null hypothesis. Now this is a true distribution. This is where the distribution is coming from. But now we are saying, let's say we are assuming that the null hypothesis is mu equal to 48. Now it seems that if the null hypothesis is 48, this means that this calculated area, which is this region over here, if we calculate it, it turns out to be that alpha is 0.17, which is lower than, you know, than what it should be, right? What it should be 0.05. And if we test, and again, the null hypothesis, so basically here, if the sample mean turns out to be in this area, we reject the null hypothesis, right? And when the null hypothesis we are testing is 56, which is somewhere over here, right? So it looks something like so. I'm sorry, this should be like very similar, very much symmetric. But if the value turns out to be over here, we're rejecting the null hypothesis. But, you know, like, you know, if the mean turns out to be here or there, and if we calculate this alpha, it turns out to be that this alpha is equal to 0.85. Okay. I'm sorry, I did something wrong here, because basically this is 53, 56 is somewhere over here. So I'm gonna erase this, and I'm gonna keep this on the video just so that you learn from me. So 56 is not here, 56 is somewhere there. And basically you can see that the majority of the distribution is outside these critical values that we spoke about earlier, where the distribution is actually generated over. So all this region over here is going to be the alpha. And in this case, what is a p-value? The p-value turned out to be, it's going to be 0.85. So you can see that if I'm going to be plotting the p-value as a function of mu, which is the mean, if I'm going to be plotting the p-value as a function of mean, so this is a mean mu, so this is mu taking the value of 50, 52, 50, 56, and this will be the value of at 48, mu equal to 46. It turns out to be, if you plot the p-value, it will turn out to be that it is going this way until it reaches 54, which is 0.05. The p-value is going to be 0.05, and then it goes up again. Right? So what does this mean? This means that the p-value, when we are testing for the true null hypothesis, should be equal to 0.05, which what we expect. And when we are going to be larger than that or smaller than this value, which is a true parameter, which the data has been generated from, then the value might, the p-value is going to be more. And that's a problem, right? Because we really want it to be 0.05, not any value that is beyond that number or below that number. And this function is known to us as a power function. Okay. This is a very better drawing than my drawing. When we are, this picture is taken from Basic Econometrics book in the appendix, and this somehow illustrates the probability of rejecting the null hypothesis when the null hypothesis is it's true. So basically you can see that when the scale of mu, which is the mean, is equal to 50, then the probability of rejecting it is going to be 0.05. So basically you can see that this is 0.05. So this is a true kind of thing that we are really seeking for. However, what we can see is that the true value of mu, which is the mean, the population mean, differs substantially from the hypothesis under the consideration. So the probability of rejecting the hypothesis is high, but when the true value is not very different from the value given under the null hypothesis, which is, the 50, we can see that the probability of rejection is small. So it's not that far from the 0.05. You can see that if we were 48, which is very close to 50, then the p-value is not that big in consideration from 0.05. It's about let's say here 0.18 or 0.15, which is very close to 0.05. So as you can see, as we move on from, from the right-hand side or from the left-hand side, from 50, we can see that this is rejecting the null hypothesis when the null hypothesis is what is true. So the power of the test, the more you were able to move, this is somehow how much it is deviated. So if we are doing two tests and it turns out to be that the other test turns out to be, you can reject the null hypothesis, or the p-value of the null hypothesis is going to be much more smaller, as you can see over here. So it is way much more smaller. Then you can see that we are going to be rejecting the null hypothesis when the null hypothesis, we are more likely to reject the null hypothesis when the null hypothesis is not true. And this is more powerful. The red curve that I draw to you right now, which is this one, or the green curve now, it is going to be more powerful than the one with the black color, okay? So we really care about the power of the test, as you can see over here. And the more this is tight, the more, the more powerful this test is. Now let's go to the Monte Carlo experiments, and this is a very important experiment in econometrics, especially for those who want to go into the theory and try to understand why are we, rejecting the null when the null is true, and and all of those kind of things. So we really need to study, the power and the accuracy and the biasedness. All of these things could be studied when we run Monte Carlo experiments, and this is the main idea behind our tutorial that you're gonna be having today, which is this exercise. So it's a simulation exercise because it involves a lot of a lot of the ideas we just spoke about. How to test a hypothesis, how to test the power or the accuracy, and all of these details that we want. So let's start with talking about the Monte Carlo experiments. So previously we showed that under the assumptions of classical linear regression models, that the least square estimators have certain desirable statistical features summarized as the blue, which is the best linear unbiased estimator. In practice, how does one know that the best linear unbiased estimator property holds? So this is definitely need to be done through Monte Carlo simulation. So Monte Carlo simulation is just, you're repeating the same experiment over a number of observations. How does one find that the OLS estimators are unbiased? So let's start by explaining how to do this. The answer is to provide a Monte Carlo experiments which are essentially computer simulations or sampling experiment. Consider the following model. Okay, so let's consider this model where we have yi to be equal to beta 1 plus beta 2 xi plus ui, and I'm gonna illustrate this using Excel, but obviously you can do that in TSM, but I just think it's better off to start things with Excel and to show you how things are really done. So you understand how, what do you mean by experiments and what do you mean by simulations. So here we have observations, okay? We have 25, we're assuming that small n is equal to 25 observations. And we have these are the residuals. So these are the residuals are generated from a normal random variable of mean 0 and variance 1. And we have for each and every experiment we have 25 observations of the residuals. So this is residuals first experiment, this is the second experiment, this is the third experiment, fourth experiment, fifth experiment, and sixth experiment. And let's say we have, observed these x variables, okay? And we are looking at y's. Now you can see that here y's are not constructed yet because they really depends on the fixed regressors. These are fixed regressors. And here is each and every experiment. For the sake of clarity, let's define, beta 1 here is equal to 20. So basically our model look like yi is equal to 20 plus 0.6, xi plus ui. And as you can see that, as I showed you in the Excel file, that these are somehow constant. However, these could be changed from one experiment to the other. Okay, so if we look at the Excel file that I just showed you here, and we would like to generate, the yi's. Okay, the yi's would be equal. So beta 1 is equal to 20 plus 0.6 times x, which is this observed value x, and this should be fixed. So I'm gonna put, so this are gonna be fixed, plus the error term, which is available over here. So this would be your value, your observed value of yi. This should be it. Now, if we do the same thing for the second one, which is, you can see that this is completely adding the right numbers. So you see that this is beta 1, this is beta 2 times the observed variable over here times x2 times plus the error term ui2, which is which is given as follow, which is here, I think, which is here. You see this is the error term. And we do the same thing for each and every one of them, of the 25 observations. So we do this for the 25 observations over here. And when it comes to, going to y2, this is the experiment number 1. So these are the y's, the observed values of y's for experiment number 1. For experiment number 2, we have to do the same thing. So we have 20 plus 0.6 multiplied by x, which is this value over here, plus the error term over here. So it's error term number 2. Okay, and we press enter. And if we do the same thing for all of them, then you have this is your second observed dependent series. Okay, these are artificial samples that have been generated based on a fixed series of x, and you have these as your experiments. So this is these are your results of your first your simulated experiment from experiment number 1. So here I'm gonna write experiments, and this is experiment number 1, experiment number 2, experiment number 3, 4, and 5, and 6. So obviously you can do 1000 experiments, but here I'm just confining myself with experiment number 1, 2, and 3. And we do the same thing here for 20 plus 0.6 multiplied by x, plus the error term, which is of experiment number 3, and we press enter. So this will be your result over here. If we continue doing this for all the values over here, you will see that for each and every experiment we have y's and we have the same x. Now what we want to do is that we want to run the regression of this on that. So this is your dependent variable, and this will be your explanatory variable, right? So if you run these regressions on one another, and obviously on the intercept using TSM, you will find out that you will have how many betas? You will have, for this, you will have beta 1 hat, beta 2 hat, right? So you will have something like so. So you are going to be having beta 1 hat for experiment 1. You will have beta 1 hat for experiment 2, beta 1 hat for experiment 3, and so on. And obviously you're going to be having beta 2 hat for experiment 1, beta 2 hat for experiment 2, and beta 2 hat for experiment 3, and so on. And basically what you want to do is, that the mean of this should converge to what? Should go to beta 1, which is the original beta 1, which is, in our case, it's equal to 20. So if you take the mean across all the experiments of the beta 1 hats, you will find out that this is equal to beta 1, or at least it approaches to it, depending on the experiments, and of course depending on the sample size. When I say sample size, I mean by it to be this kind of 25 observations. So here we're assuming that when we are running a regression, we have only 25 observations. However, when you have more observations, we're assuming that the beta 1 hat is going to be more likely to approach beta 1. And this is basically the main idea of your exercise over here. This will be your main idea of the experiment over here. So here you are being asked to investigate the properties of least square estimator, right, in different sample sizes. So you're gonna be generating the error terms, and obviously here you can see that alpha is equal to 5. So this is the intercept. This is equal to 5. This is equal to 1, and this is equal to 0.05. And these are the error terms, and the error terms are normally distributed with standard error 1. So they are mean 0 and variance 1, okay? And you need to report on the bias of the estimator and so on, and the accuracy and the power. So I believe I explained what we mean by accuracy, what we mean by the bias of the estimator, what we mean by the power. And the question is, do they really reject at 5% of the time when the null hypothesis is true? So we look at the p-values, right? And if the p-value is very close to 0.05, this means that we are more likely to to have the right null hypothesis. Do they reject much more than 5%? Then this becomes, this becomes that we are rejecting the null hypothesis when the null hypothesis is true, and this becomes a problem. Okay, now I believe that majority of the time you will find that it is 5%, but obviously this will change from, from the sample size from 10, 30, and 100. Now, actually, I've run the regressions over here. Now, you can run the regressions easily by following the steps here in TSM, how to interpret your results, how to run the experiment. Everything is well explained, but for the sake of argument and for the sake that we need to explain this stuff, I'm just gonna show you some of the results over here. So here I was running the experiments for the mean. So this is the intercept, this is the x series, this is the y series minus 1. You can do this in TSM. These are the outcome of TSM. And you can see that the mean is somehow very far from 5. Remember that the mean should be equal to what? The mean should be equal to 5, right? This is intercept. So you can see that the intercept over here is about 8 when we have 10 observations, right? So here you can see that we have 10 observations. We are taking them from 51 to 60, and we run experiments. Okay, and it seems that this is a true parameter. So this is a true parameter, and this is the estimated parameters. So these are the means, if you want to say, of the betas that we spoke about earlier. So if you remember what we have spoke about these betas, so the mean of these betas is gonna be equal. So I'm gonna call it beta hat bar. These are the mean betas. You can see them; they are over here. This is going to be 8.1. And remember, this is of sample size only for 10. So this is only represented by 10, and we are running about 100 experiments. So having said that, we have to look at all of those ideas, and what we found out is that the intercept, these are the p-values, or no, this is the p-values. We found out that the intercept is about 0.08 at a 5% significance. So the true parameter should be 5%. We are at 8%. So we are more likely to reject the null hypothesis when the null hypothesis is true. But it is fairly close. But this is only with 10 observations. If we go again to the question and we found out what about more observations, what will happen when we have more observations? So the next experiment is we have 30 now. If we run with 30 experiments, 30 observations, you will see that our intercept is closer to 5. Our beta, which is here, as you can see, beta is equal to 1 and lambda is equal to 0.5. You can see that this is very close to 1 and this is very close to 0.5 with 30 observations. So this is 28 observations, the same as 30 observations. And you can see the results over here. I will attach this file to you so that you can compare when you do your simulations. You can see that this is 5%. This is at a 5%. The bias is 1.09. Okay, I'm assuming that here we are having 28 observations. The bias is very small. Remember, the bias is defined as beta hat minus the true parameter beta. And you can do this all to other experiments as well. For example, here when we have larger sample, okay, when we have 28 observations as well here, but we have more experiments, you can see that these are changing from time to time, like depending on, here for example we have 100 observations. So now we are in this category, 100 observations. You will see that these values are getting closer and closer to the true values, which is 5 and 0.5, and this is 1. This is X series. And the p-values are given as you see now that we are very close to the true parameter. We can see that the p-value are very close to the true p-values of the test. You can see for all the experiments, the p-values should be very close to that of the 5%. So I'm not gonna go through all these details because I think it's better to solve different things next tutorial. But I think it would be very important exercise for you in TSM. But this is not graded assignment, so don't worry about making sure that you want to solve it. It's just understanding the main concepts that I just raised here. That this is fixed across samples, across experiments, and this is what I really want you to take out of this lesson, and to understand how Monte Carlo simulations are being run. Okay, so I'll see you all next